Hi everybody, nice to meet you again. I hope everybody is in good health. Right, before we continue with our discussion on topic of shallow foundation, I would like everybody to have a yellow book with you because we have to refer to certain equations in this book, pen or pencil, as well as additional sheets of paper, because I believe the perfect way to learn is by a combination of listening, looking, and writing. Right. Okay. To begin with, I would like to recall what we have discussed in the previous lecture on the topic of shallow foundation. Right. We have equations by Terzaghi. By Terzaghi, we have three different equations depending upon the shapes of the footing or the shallow foundation. Whereas we have a long equation by Meyerhoff-Hansen, which cover different shapes of foundation. Right. Today I would like to give you example how to use those equations. One example based on Terzaghi's equation and another example by Meyerhoff-Hansen's equation. Okay, nanti dulu. Okay, this is the example that I'm going to work on. So I hope everybody will copy or will write down, and then I'll show you the steps how to solve this problem. Okay, this is the first example that I'm going to show you. Alright, I hope everybody will write down the diagram and the problem statement. Then I'll show you how to solve this problem step by step. Okay, in this problem, we have a shallow foundation which is a square with the dimension of 2 meters by 2 meters, and the depth of the foundation is 1.5 meter. These are the soil properties. Unit weight equal to 18 kilonewton per meter cubed. Cohesion C equal to 30 kilonewton per meter squared, and this internal friction angle equals to 30 degrees. Okay, according to this problem, we have to use Terzaghi's equation to determine the following. A, the allowable bearing capacity, small q sub all. B, net allowable bearing capacity, small q sub net all. C, allowable load, capital Q sub all. D, net allowable load, capital Q sub net all. So in these problems, we have to use safety factor Fs equal to 2.5, right? So if we refer back to our previous lecture, Terzaghi formulated three different equations depending upon the shape of the footing. Now, if we refer to this diagram, it's a square footing, then you have to refer in your book, page 22 or 23, you refer to equation for rectangular footing. Okay, if we refer to this problem, right, this example, so we have a footing, square footing, 2 meters by 2 meters, and then the depth of footing is 1.5 meter. These are the soil properties. Unit weight or gamma equal to 18 kilonewton per meter cubed. Cohesion C equals to 30 kilonewton per meter squared, and the internal friction angle phi equal to 30 degrees. Right. So, in this statement, we have to solve the problem using Terzaghi's equation. Right? If you remember what I said in the previous lecture, we have three different equations formulated by Terzaghi based on the shape of the footing. Now, if you refer to your yellow book on the page 22, you have to refer the equation for rectangular footing, because square footing is included in the rectangular footing. Okay. Okay, this is the equation that we are going to use. If you refer to your book on page 22, so you refer to the rectangular footing, right? This equation, Q sub U equal to 1 plus 0.3 B over L multiplied by C multiplied by N sub C plus Q multiplied by N sub Q plus 1 half 1 minus 0.2 B over L multiplied by gamma B and gamma. So based on this equation, we collect or we obtain the values that we can refer to the book, such as the value of N sub C, N sub Q, N sub gamma, which depend on the value of internal friction angle. Right. If you refer to your book on page 59, for friction angle equal to 30 degrees. Okay, everybody refer to your book, page 59, table for Terzaghi's bearing capacity factors. Right? For friction angle 30 degrees, N sub C equal to 37.16, N sub Q equal to 22.46, and N sub gamma equals to 19.13. Alright? So since this footing is a square footing, then square footing B is equal to L. Right? B is the width of the footing and L is the length of the footing. So for square footing, B equals to L. Right? So we rewrite this equation. It becomes Q sub U B over L equals to 1. Then in this parenthesis, 1 plus 0.3 becomes 1.3 C N sub C plus Q N sub Q plus 1 minus 0.2 B over L. B over L equals to 1. Then 1 minus 0.2 is 0.8 divided by 2 becomes 0.4 gamma B and gamma. Okay, we insert values into this equation. So Q sub U becomes 1.3 multiplied by C. If you refer to the diagram, cohesion is equal to 30. N sub C is equal to 37.16 plus Q. Q is the stress at the base level of the footing, meaning you. So you'll get this value, 2331.13. So for this ultimate bearing capacity, the unit is in terms of stress or pressure, which is kilonewton per meter square. Okay. After this, we have to calculate or to determine the Q allowable, Q net allowable, capital Q allowable, as well as Q net allowable. Okay, let's calculate the allowable bearing capacity A. Allowable bearing capacity, small q sub all represent allowable bearing capacity, which is equals to the ultimate bearing capacity divided by safety factor. Q sub U, that is the ultimate bearing capacity that we have calculated before, and then divided by safety factor, which is 2.5. So Q allowable becomes 2331.13 divided by 2.5. Here the unit still in kilonewton per meter squared. So we'll get this value, 932.45 kilonewton per meter squared. That is the allowable bearing capacity, which is ultimate bearing capacity divided by safety factor. Okay, let's move on to B to calculate the net allowable bearing capacity. Okay, net allowable bearing capacity Q sub net all equals to Q sub U minus Q divided by safety factor. Q sub U is the ultimate bearing capacity that we have calculated before. Q, this is the stress at the base of the footing, which is an item in the ultimate bearing capacity equation, and then divided by safety factor, right? Q sub U, which is equal to 2331.13, and then minus Q. As I mentioned before, Q here is the stress at the base of the footing due to the weight above the footing. So it's unit weight of the soil, which is 18, multiplied by the depth of the footing, 1.5. Okay, I write down here, 18 is representing the unit weight of the soil, and 1.5 meter here is the depth of the footing. Okay, generally, this Q, stress at the base of the footing, is due to the weight of the unit weight of the soil multiplied by the depth of the footing, right? And then we divide by the safety factor here, 2.5. Then we should get this value is equal to 921.65 kilonewton per meter square. That is the net allowable bearing capacity. Okay, let's calculate the allowable load. Capital Q representing load, sub allowable, so it becomes allowable load, which is equal to small q allowable, or the allowable bearing capacity, multiplied by the area of the footing A sub F, right? So this q allowable we have calculated in A, right, which is equal to, if you refer back to your notes, 932.45. So 932.45 multiplied by the area of the footings, 2 meters by 2 meters. So we should get 3730 kilonewton, right? So Q allowable, the unit is in terms of pressure, kilonewton per meter squared, and then multiplied by the area, the unit is meter squared. So meter squared cancel, so the final unit is kilonewton, right? Now, finally, we calculate the net allowable load, capital Q sub net all, which is equal to small q net all multiplied by the area of the footing, right? Q net all, you refer back to part B of the example, so which is equal to 921.65 kilonewton per meter squared multiplied by the area of the footing, 2 meters by 2 meters. Then the final answer here is 3686 kilonewton. Just like in C, the final unit is kilonewton because Q net allowable, here the unit is kilonewton per meter squared and area is of meter squared. So meter squared and meter squared cancel, so the final unit is kilonewton. Okay, this is the example. Okay, before I show you how to solve this problem, so everybody take your time to draw the diagram and write down all the soil properties and the problem statement. Okay, in this example, we have a shallow foundation of footing with the depth of footing is 2 meters, and then we have unknown dimension on the footing, a square footing, B multiplied by B, and these are the soil properties. Unit weight, kilonewton, 18 kilonewton per meter, sorry, should be kilonewton per meter cube, right? And then the internal friction angle of the soil equals to 33 degrees. the cohesion is equal to 0. So when the cohesion is equal to 0, meaning the soil here is granular material or non-cohesive soil. Okay, on top of that, this footing is subjected to an inclined load, Q allowable, that is allowable load, equals to 2000 kN, and this load is inclined at an angle of 80 degrees with respect to horizontal. Right. So which equation that we have to use to solve this problem? If you refer to the three Terzaghi's equation, straight footing, rectangular footing, circular footing, those equation doesn't take those three equations don't take into account the angle of the load applied to the footing. So in that case, we have to use Mayhoff-Hansen's equation, because this equation take into account the inclination of the load. Okay, if you look at this example, okay, we have a footing with a depth of 2 meters, and then this footing is a square footing, B multiplied by B, right? And then these are the soil properties. Unit weight gamma equal to 18 kN per meter cube. Internal friction angle equals to 32 degrees. C, or cohesion, equal to 0. So when C equals to 0, it shows that this soil is granular material or non-cohesive soil, right? Okay. So this footing is subjected to an inclined load. Q allowable equals to 2000 kN, inclined at an angle of 80 degrees with respect to the horizontal plane. Right. So in this problem, we have to determine the minimum dimension B. So we have to determine B. What is the dimension of the footing? And then if the safety factor is equal to 2.0. So in this case, we have to use Mayhoff equation, because Mayhoff equation takes into account the inclination of the load. Remember that in Terzaghi's equation, those equations don't take into account the inclination of the load. They assume that the loads are vertical. Okay.